I'm happy to be here representing our group from Ghent University in Belgium. And I will tell you how we are using LCMS-based metabolomics to try to determine the function of secondary metabolite gene in Aspergillus flavus. In fact, we are pretty much interested in using a number of different tools to try and explore natural products and more specifically secondary metabolite. So we are pretty much interested in secondary metabolites because of their ability to manipulate biological systems. So fungal metabolite, for example, can have antibacterial or anti-proliferative activity, but they can also have some detrimental effects, as is the case for aflatoxin B1, which is one of the most potent mycotoxin, a potent carcinogen produced by fungi. So secondary metabolites are produced by many organisms to help in their growth or in their development, but they're not required for their survival. And we think of them as being evolutionary driven to be synthesized, and they're strictly diverse because of evolution. So we are interested in Aspergillus flavus, and this is the fungi that is mostly known for the production of aflatoxin, and as I say, is a potent carcinogenic compound. So in recent years, we have learned that the gene for secondary metabolites are clustered. So with regard to Aspergillus flavus, we know that there are 55 gene clusters that are predicted to be associated with the production of secondary metabolites. And so we could expect up to 55 distinct metabolites from this fungi. But until now, only about less than 20 metabolites have been found in extract of Aspergillus flavus. So the likelihood that we'll continue to discover new active compounds from this fungi is really high. On the other hand, among the metabolites that have been already found, those less than 20 metabolites, the relation between the metabolite and the gene for the production of the metabolite have been made only for 3 metabolites. So we have started a collaborative study to examine some of this gene cluster and determine the capability of and role in producing known as well as unknown secondary metabolites. So there are several reasons why in previous studies people didn't find all those metabolites produced by the fungi. The biosynthetic gene might not be turned on under the condition in which the exploration have previously occurred. And also, probably the technique that were used failed to detect this compound, either because they were low abundant, or in case of bioassay, because the compound were not bioactive in the assay that were utilized. So there are different strategies to try to induce secondary metabolite production. People can do gene inactivation or overexpression. People can also do heterologous gene expression, or you can use various culture conditions or co-culture. So we're using gene manipulation. So the idea is to create a deletion or overexpression mutant and apply comparative metabolomics to try and detect and identify the compounds that are differentially expressed. So I think that for this audience, these are the challenges related to the metabolomics, but I will not go through this. What I would like to say is that the workflow we are using, so the fungi are grown and the metabolites that they produce are extracted. We typically use a generic extraction to try to get as many metabolites as possible. And then we'll do the LC, and we're using reversible phase liquid chromatography using a Zorbas column, which actually showed in our experience a very good retention of not only apolar but also polar compounds. And for the detection, we are using the orbitrap exactive, but also the triple-TOF MS instrument. And then after running the sample, we get a complex three-dimensional data set for each sample, and we use differential software to try to analyze those data. So typically there are two steps in our approach: the profiling, where we look for features and differences in groups of samples. And in case of the orbitrap instrument, we use the sieve software. And for the data acquired with the triple-TOF, we are using MarketView software. And then we try to identify the metabolite produced, the different metabolites. And the identification starts typically with database search, and we search against database containing non-metabolites using the accurate mass data. But we also then we get a kind of putative identification, but we go for CID experiment for confirmation. And when we have that putatively identified compound, we try to acquire the compound and compare its behavior versus the behavior of the unknown, and thereby I mean accurate mass, retention time, and fragmentation pattern. So by combining this different piece of information, we get a kind of confident identification of the compound based on LCMS data, but most of the time we also try to confirm the identification of the compound using NMR after purification of the compound. So I'll just go through two of the examples of the gene cluster for which we try to identify the metabolite produced. The first example will be on a knockout gene, and the second example on a overexpression. So among the 55 gene clusters that are predicted to produce secondary metabolite in Aspergillus flavus, half of them might be silent. So we selected one of the gene cluster which were found to be active under normal laboratory growth conditions, and we applied our metabolomics approach. And what we observe directly is the change of phenotype between the wild type and the mutant. And we want to know which metabolite was responsible for this change by using our UHPLC HRMS approach. So we applied, as I mentioned, we applied sieve software to try to reveal the metabolite that were differentially expressed. And here I just show, finally, after applying this software, I show in the total ion chromatogram what are those metabolites that we found that were differentially expressed, the most important metabolite. And when we tried to do a database search, we could identify one of the metabolites, this one, is asparagine A, and we confirm this by acquiring the compound and comparing the retention time and the MSN data. But for the three other compounds, we didn't get any hits in databases. So, but we say these compounds are produced by the same gene cluster, so they must be from the same pathway and they must be related. Then we say we're going to study the full fragmentation pathway of the non-compound asparagine, and based it on this fragmentation pathway, we are also going to do the fragmentation of the unknown compound and try to do some kind of correlation to see where this compound fits and identify those compounds. And indeed, these are just to show in summary how the fragmentation of the two of the compound fit the fragmentation pathway of asparagine. So one of the main fragments that we found in asparagine was this fragments of mass 297, and we observed that the two of the metabolites, the unknown metabolites, join this pathway at this level, but one of the metabolites, the compound one, were showing always a difference of 16 Dalton throughout the pathway, which actually we could attribute to oxygen or a hydrogen replaced by a hydroxyl group. So based on this information, we were able to assign the different compounds. So this is the structure of asparagine A, and based on the fragmentation pattern, we were able to assign compound 1 as a hydroxy derivative of asparagine at this level, and compound 3 is asparagine lacking the acetyl part here, while compound 4 was a dehydrated derivative of asparagine. The second case is a case of expression. So one of the gene cluster were found, or we thought that it was inactive under the normal growth condition. So we created a organism with a strong promoter, the GPD promoter, put in front of the transcription factor for that gene cluster, and we want to know what was the effect on secondary metabolite production. And when we compared the wild type and the mutant, PCR analysis showed some of the compound mass that were differentially expressed in the wild type versus the overexpression mutant. And we also made different knockout, and one was the knockout of the backbone gene of the cluster, and PCA also indicated that the same mass that I just showed in the previous slide were responsible for the separation of the three groups of samples. And this is just the extracted chromatograms of some of this compound. And what we observed is that some of the this compound that we saw existed as dimer. So as you can see, for example, for this compound with mass 703, when you look at the MS2 spectra, you see that the region here correspond exactly at the spectra of the compound 352, which, so this the region here correspond exactly to this one. So this was actually a confirmation that some of these compounds exist as dimer. And based it on database search and some a priori information we had on genome analysis, we could identify this compound as leporin B, and we could confirm this by first of all by MSN data, but also later we confirmed this with NMR analysis. And one of the compounds we found also to be expressed in this cluster was the compound with mass 336, and we applied the same approach as we could identify easily leporin B based on the knowledge we have, and by comparison with a standard. The standard was a standard of leporin A. We did also a full fermentation, and we established the fermentation pattern. And here I just show you the general pattern that we observe. So we observe again here the same mass neutral losses, and with always a difference of 16 Dalton, which we finally could attribute to the fact that the compound, the unknown compound, was lacking the hydroxyl group here, which was replaced by a H group. So we could identify this compound as a dimethyl leporin A. So to conclude, we are really excited in using UHPLC hyphenated to high resolution MS as a suitable tool in comparative metabolomics. So we applied this tool to discover novel compound and low abundant compound in samples, but also to assign the gene involved in the biosynthesis. And we would like to extend this to some other gene cluster of Aspergillus flavus, but also to other fungal species. So these are the different people who collaborated in this work, and I would like to thank you for your attention.
You mentioned in your introduction that one of the techniques that you can use is co-culture. Yeah. So how do you actually go back and work out which of the microorganisms has actually triggered the pathway once you've done that?
Yeah, yes, this is what I meant is that, yeah, you just I have to say that it's not so evident, but we try to try to compare what we see by culturing the compound alone, I mean the fungi alone, but also with what we know from the other individual fungi. But I know that so it can come from.
So is it just a case of intensity? You actually get more by co-culture, and then you go back and you check the organism alone, and in most cases it's there, but at very low levels. Or
yeah. Yes. Yeah. It's to try to to enhance a little bit the production.
Any other questions?
Thank you. In most of the structures that I have seen during your presentations, I believe there is a lots of asymmetrical centers. I'm talking about the stereochemistry.
Yes.
And probably there is not a chance to using reverse phase to separate diastereomers. I would suggest why don't you try helic. Hydrophilic chromatography sometimes makes very good difference.
Yeah, I have to say, first of all, I have to say yes. In general, we had a lot of problems. I have to say we have a lot of problems being successful with.
No, it's not a problem. It's just working situation.
Yeah. Okay. We had a lot of trouble using helic.
How good are the predictions from genes from the modular polyketide domains to be able to predict the compounds?
No, what I mean is not really predicting the compound. What we do, we just do blast. For example, the case is the case I say the case of leporine. This case here. What we did actually when we did blast of the sorry? Yes. So we base ourselves on the polyketide, for example. So we do a blast. For example, in this case, when we did blast, we found that the best match corresponded to some compound described in the literature. After the best match produced as compound the 2-pyron compound, this kind of structure. And when we looked in the literature, we found actually that one of the compounds produced by Aspergillus flavus was actually leporine A, which we didn't, which was not here, leporine A. So it was actually this, what helped us to find the structure based on the difference. Leporine A is fatty mass Dalton higher than this compound, but by deducing and by looking at the spectra, we could finally deduce the compound.